All right, cool. Well, welcome back. So next up on our reunion tour or our victory lap, we're actually going to be spending a bit of time building up some notation as well as some terminology in the wonderful world of graphs. So these cool little machines are actually going to be the backbone of many of our future algorithms as well as general discussion of efficiencies and what they can actually do. So let's actually go ahead and jump on in. So down below, you can actually see one of these cute little graphs. This particular thing's got what? About 20 or so nodes or vertices. I've actually labeled them to make the counting pretty easy. It's going to start at 0 and go all the way up to 19. I don't believe I have a 20 in this one, so it's going to go all the way up to 19, meaning that I have 20 total nodes or vertices and some number of edges. I did not label those things. I also don't feel like counting those things right now, but later we'll have some ways to count that up to make that obviously a little bit easier. But for right now, we're going to have some number of edges that are going to be connecting these things. So before we go too far into this kind of world, I'm actually going to double back to a cute little Scandinavian proverb. So last time you got a nice little Dr. Seuss quote. Here you get a fancy Scandinavian proverb, which goes of the following form. So it's going to say, go often to the house of thy friend, for weeds soon choke up the unused path. So down below, I got a nice little visual interpretation of that, and that I have Bob hanging out over here, and I'm going to have Alice hanging out over here. Obviously, there's a nice little path between them that is not littered with weeds. Here are my best drawing of weeds, obviously on the outsides of the paths, which is clearly meaning that Alice and Bob go visit one another very often, exchange a variety of nice, cool messages in various encrypted methods. More about that a little bit later, but it's a cute little picture, and hooray, that's about as good as I can get. But you've already seen some terrible pictures, so you already knew my skill set there. All right, back to the cool graphs. Hooray! All right, so here's a graph. It's got 20 vertices on it. It's got a whole bunch of questions that can obviously be poked into it. The very first question, kind of the most natural question that leans off of that cheesy little proverb, is simply going to be a question of reachability. Basically, if you give me two nodes on this particular graph, so let's say if I have 0 and 8, both of those live on this particular thing, I simply want to know, is it possible to get from that initial node over to that final node? And it's worth dwelling at this point in time that these graphs can represent pretty much anything that we want them to actually represent. I could genuinely think about this as being this nice Scandinavian village that's going to have 20 total families. And then these little edges are going to basically be whether or not there's a genuine real life path that connects one little house to another house. So then it becomes this question of, can I get from 0 to 8 or from Alice to Bob without having to essentially go off-roading? I could also then increase this as general questions of cities or villages that are going to be interconnected with one another. I can view this as whatever type of network I'd want to think about this, where I'm going to have various edges that are going to represent whatever type of connection you want to think about. This particular graph does not have any additional rules on it in terms of how can I actually go about these particular edges. Later on, we're going to begin giving these things some directionality or a flow, which is then going to mean that I can only go, in a certain direction. I can go from 0 to 14, but I can't go the other direction. Obviously, if this is some type of network and we're actually chatting about water flow, there's not going to be the ability to go against the current, but I have to go whatever direction it's going to tell me. This particular one does not have any of those rules, so it makes my life really nice and easy. So then my first question, as we've alluded to, is just simply going to be a question of, can I get from point A to point B? So can Alice go visit Bob without having to, cut across some random field? Here you can see the answer is yes. There's a variety of different ways that we can actually connect these things. I can do what? The 0 to 9 to 16 to 1 to 8. That particular path has length 4. I could also do what? I think the other one that I have sketched out is I can go to 11. I can then go up to 3 maybe, and then over to 13, up to 17, and then down. That particular path has length 6. Let's do one more, just because I got one more drawn in the notes. And since I'm going to show it to you in a second, I might as well have it sketched out here as well. I could do kind of the big dumb outer one. I can go to 14 to 19, over to 5, and then maybe I guess down to 1, and then up to 8. That particular path has length, what, 5? So you can see that there's a different kind of flavor depending on how I go about this. You could also take some kind of really dumb paths and that you could do something like 0 to 14 to 4 to 10 to 14 to 4 to 10 to 14 to 4 to 10 to 14, and then spring loose and then eventually come back. I don't remember how many times I went around the little triangle. So that path has length more than 5. And depending on how many times I went around the triangle, I'm going to be adding on 3 more along the way. So obviously this question of reachability becomes that first kind of easy question of just genuinely, can I get from point A to point B? The natural follow-up question to that thing is not simply just a question of can I get from point A to point B, but can I do it most efficiently? So I didn't have it highlighted down there, but we'll allude to it in a bit, which is then going to be this question of, is there a shortest possible path? So in that example that we just did, we had 3 different routes. They had 3 different lengths. So I had one that was length 5 and we had one that was length 6. Obviously the length 5 one is going to win in the quest for shortest. But then I also had this nice little mac and cheese yellow one across the bottom that happened to have length 4. So that one wins between all 3 of these things. So the moment I have a question of reachability, the very obvious follow-up question is then, is there a most efficient way to get from point A to point B? In this particular graph, we don't have any edge weights going on. So it's simply going to be a question of how many edges did I actually have to use. Later on, we can actually easily put some type of value to actually use that particular edge. So some type of toll, if I want to think about it as kind of costing me money to go across this thing. Or I can think about the little numbers as simply just being distances. This picture may not be drawn to scale. So let's say that this is, 100 miles, and then this is going to be 20 miles. Well, obviously going from 6 to 16 is then way more expensive than going from 16 to 1. But in our scenario, there are no weights on this thing. There's no directionality. It's simply a nice little graph, which when I'm start chatting about shortest path is really just going to be a question of how many edges did I happen to use. So here you can see that there is exactly one of those 3 paths that has length 4, but it's not the only path that happens to have length 4. There's actually 3 of them that actually have length 4. And you can start to see how they're going to be sketched out by basically looking at where can I get to from the 0. From the 0, I can get to the 14, the 11, and the 9. On the back side, to get to the 5th or to get to the 8, I had to have either visited the 15 or the 1. So if any of those were connected, we'd obviously see paths of length 2. But 14, 11, and 9 are not connected to 15 and 1. So what you can start to do is you can basically begin branching out a little bit more. Well, to get to 15, you'd have to be at the 17 or the 12. And to be at the 1, you'd have to be at the 13, the 12, the 18, or the 16. On the other side, well, from the 14, I can get to the 19, I can get to the 14, and I can get over to the 13. And from the 11, I can actually get up to the 4, I can get up to a 5, I can get over to a 3, to a 12. And then from the 9, I could get to a 7, and I could get down to the 16. So here you can actually start to see how these paths are going to be formed. So if I begin to erase these, you can kind of start to see how they would have ended up shaking down. So I think I might have actually forgotten one. Now that I drew it all out, I might have actually realized that there's one more. I think I lied to you. I said there was 3, but there's actually going to be 4. So here's 3 of them, and I'll quickly draw in the last one that I just realized as I was sketching it all out. So I have the 0 to 9 to 16 to 1 to 8. I have the 0 to 11 to 12, and then there's 2 other paths away from that. So 12 to 1 to 8, and then 12 to 15 to 8. But there was actually another one too. I can go up to 14, over to 3, over to 13, and then down to 1. Oh, nope. Okay. I was totally fine, I think. Maybe. Let's go back. I thought there was one that I got. Maybe it was just too many colors and I've already erased it now. All right, let's stare at it for a sec. All right, so if I went to 14, is there any way that I can get to the 8 in 4 clicks? Yes, I can. If I go over to 4, that's the one I was missing, down to 12. Nope, that's still too many. All right, maybe I'm not lying to you. Maybe I was totally fine beforehand. 14, The only thing I can get to from there are those, and none of those things are 2 away from the actual 8. I can also get to there. But none of those things are actually 2 away from the 8. So I think I'm totally good. I might be bad. We'll check on the actual filled out version of the notes later. So if I do end up finding my other one, I'll adjust it. Otherwise, we're just going to keep on going with it. Later on, we'll obviously be chatting about different ways to do this that don't involve me just trying to doodle on a board, because that's obviously going to go poorly. But we'll start to see those things come in a little bit later. So that's our first kind of starting place, is our chat about general questions of can I get from one point to another? And then leading it into the very natural second question of, is there a most efficient way to get from one path to another? What we want to obviously begin leaning on a little bit is going to be, how do we actually make use of some algorithms to actually solve those questions for us? We're going to need a little bit of discussion about how we're going to encode these things. Once we have them encoded correctly, we can then just run through our favorite, breadth first or depth first searches and do all kinds of cute things from that as well. So I'm going to pause it right now. We're actually going to chat into the world of how do we actually want to begin encoding these things, and then actually do a few of these little searches, and then lean in on some code, and then call it a section.